Problem. Hello students, here is a problem on indeterminate frames solved by the method of least work. So analyze the frame shown by the method of least work. Also construct the shear and moment diagrams and sketch the elastic curve. For more examples, you just go to my YouTube channel and there are a lot of examples on frames, indeterminate frames solved by uh, method of least work, just like this. So this is indeterminate to the third degree. So I choose horizontal component, vertical component of reactions, and the moment reactions at A as the redundant forces. There are three, and we evaluate partial of work with respect to the first redundant equals 0 because this is a support that does not settle. So the assumptions are as shown so that every time we formulate the moment equation, they are always positive. So the moment at this section, these are the sectioning, you have three sections here, is equal to integral. The moment equation here is EH times X, then AV has no moment, plus MA. Then the derivative of this moment equation with respect to AH is X dx. EI is constant, so we just leave it at this. So the EI is multiplied here, but EI times 0 is still 0. Then, for the next section here, the moment is EH times 8 plus A sub V times X plus MA. AH times 8 plus AV times X plus MA. Then minus the moment of the loading, which is minus 30 times x over 2, or minus 15x squared. The derivative of this moment equation with respect to the first redundant EH is 8 dx times differential x. So that's it for that section. Then finally, in this section here, the moment is EH times 8 meters minus x, EH times 8 minus x, plus moment of AV, which is just AV times 6, vertical, then moment arm horizontal, so AV times 6, then plus MA, then minus the moment of this loading, 30 times 6 times 3. 30 times 6 times 3. Then the derivative of this moment equation with respect to AH is 8 minus x times dx. Then, evaluating integral of AHX times x dx, it is 512 over 3AH. Then, integral of x dx, 0 to 8, that's the coefficient of MA, 32 MA. Then, for the next integral of 8 times 8 dx, 0 to 6, is like 8 times 8 times 6, 384 AH. Integral of x times 8, 0 to 8, then 144 AV. Integral of 8 dx, so 8 times 6, 48 MA. Then the integral of negative 15x squared times 8 dx, 0 to 6, is negative 8,640. For the next integral of quantity 8 minus x dx, 0 to 5, is 485 over 3AH. Integral of 6 times 8 minus x, 0 to 5, is 165 times AV. The integral of MA times 8 minus x, 0 to 5, is 27.5 MA. And integral of negative 30 times 6 times 3, which is negative 540, times 8 minus x, is negative 14,850. Then combining like terms, so we have 2,149 over 3AH plus 144 plus 165 AV is 309 AV. and 32 plus 48 plus 27.5 MA, 107.5 MA, then transpose the negative constants to the right. So we have 23,490. Call that equation 1. Then the next is partial derivative of work with respect to the second redundant AV equals 0. So the first integral has no AV, so the derivative is 0. Therefore, the integral is 0. So 0 for the first. In the second integral, we copy this moment equation and we replace this derivative by the derivative of AVX, which is just x dx. Then we copy the third moment equation and we change this to negative 540. The derivative of this moment equation with respect to AV is 6. So 6 dx. Then the value of the second integral, integral of 8x dx 0 to 6, 144 AH, integral of x or x squared dx 0 to 6, so 72 AV, integral of x dx 0 to 6, we have 18 MA, and the integral of negative 15x squared times x, 15x cubed dx is negative 4860. Integral of 8 minus x times 6, 0 to 5, that's the coefficient of AH, 165 AH, integral of 6 times 6 dh, 0 to 5 is 180 AV, or that's 6 times 6 times 5, 180 AV. Integral of 6 dx is 6 times 5 times MA, so that's 30 MA. And integral of negative 540 times 6 dx 0 to 5 is negative 16,200. Combining like terms, so we have 309 AH plus 252 AV plus 48 MA. Then transpose the constants to the right, 21,060. Call that equation 2. Then lastly, partial derivative of u with the last redundant, which is MA equals 0, then equals integral, first integral 0 to 8. We just replace the derivative by derivative of MA, which is 1 dx. So dx. Copy the second moment equation, which is this. Derivative with respect to MA is dx again. Copy the third integral equation. Then derivative of MA is just 1 dx. So the value of the first integral is 32 AH plus 8 MA. For the next integral, we have 48 AH, 18 AV plus 6 MA, and minus 1080. For the last integral, 27.5 AH plus 30 AV plus 5 MA, and minus 2,700. Combining like terms, then we have 107.5 AH plus 48 AV, then plus 19 MA equals 3,780. Solving these three equations simultaneously, equations 1, 2, and 3 simultaneously, we get AH equals negative 12.233 kilonewton, so it means it is rightward. AV is 91.545 kilonewton, so it means it is upward, positive as assumed. Then MA is 36.891 kilonewton meter, so it means that it is clockwise as assumed. Then let's consider free body diagram of AB and call this MBA. Let's assume that that's the direction of the moment. So we transmit the horizontal reaction AH, which is now corrected to be to the right, 12.233 kilonewtons. So since there's no other load on column AB, the horizontal reaction at the upper end B is also 12.233 to the left. Vertical 91.545, so 91.545. So summation of moments about B equals 0, MBA plus 36.891 MA equals 12.233 times 8. So again, MBA plus 36.891 equals 12.233 times 8. And we'll get MBA to be 60.973 kilonewton meter. 60.973 kilonewton meter. And that's the correct direction. So it is clockwise. Then we consider BC and transmit the effect. So 91.545 kilonewtons. So MBA was 60.973. So we have clockwise here, counterclockwise here as we transmit 60.973. And this is 12.233 to the right because it is to the left here. So it is also to the left here, summation forces horizontal, and that's the load. So this is the assumed MCB. So summation of moments about summation forces Y, by the way, considering BC. So shear just to the left of C plus 91.545 equals 30 times 6. So shear just to the left of C is 88.455 kilonewtons. And that's also the expected vertical reaction at D because there's no other vertical load. So 88.455 kilonewtons. Then, considering the whole system, summation of moments about D equals 0, assuming MD is counterclockwise. So summation moment D equals 0. M sub D plus the moment of the load 30 times 6 times 3. Then plus, because this is rightward, 12.233 times this distance is 3, 8 minus 5, 3. So 12.233 times 3 equals moment of AV, which is 91.545 times 6 plus MA, which is 36.891. So MD is 9.462 kilonewton meter, and it is counterclockwise as indicated. Then let's check CD, if it is in equilibrium. This is CD here, CD. So summation moment about D is equal to, we already computed moment CB. Moment CB is equal to, from here, moment CB, summation moment about C, considering BC, equals 0. So MCB, which is assumed clockwise here, plus 91.545 times 6, 91.545 times 6 equals 60.973, this moment here, then plus moment of the load 30 times 6 times 3. So MCB is clockwise in BC, and it is 51.703 kilonewton meter. Then, that's it for MCB. And that's why when you check CD, column CD, summation moment D is equal to counterclockwise positive, so 51.703 plus 9.462, then minus 12.233 times 5, so it is 0. So that's why it's checks. Then for the construction of the shear moment diagram on the next slide. So remember, this is the upper fiber. So you look at in that direction, that's the positive direction for shear. Here, upper fiber is on top, so positive direction of the shear is upward. Then in this case, the positive shear is to the right because this is the considered upper fiber. So Remember, AH is 12.233 rightward, so this is negative 12.233. And constant, there's no other load, and it should close here, 12.233. Then shear just to the right of B is the vertical reaction at A, which is 91.545 minus 30 times 6, so negative 88.455 with checks. This distance is 91.545 divided by 30, 3.0515 meters. That's the shortcut. Or you apply similar triangles if you want. Then this distance is 6 minus 3.0515, so 2.9485 meters. So that we can compute easily the area. These are just triangles. Then finally, we have 12.233 shear positive in that direction. So this is positive, positive. Then minus horizontal reaction at D, which is 12.233 to the left. So that closes. So for the moment diagram, remember that MAB is in that sense. So this is the positive direction. So positive 36.891 and minus 12.233 times 8. So we have here negative 60.973. And for portion BC, it begins with this negative 60.973 plus this area, which is 1/2 of 3.0515 times 91.545, positive decreasing, so 78.702. Then 78.702 minus the area here, which is minus 1/2 2.9485 times 88.455, will get negative 51.703. Then for this portion, it begins with negative 51.703 plus 12.233 times 5. So we have 9.462 as moment at D, which is correct, positive. So that's the positive direction of moment. So this is the moment diagram in kilonewton meter. Finally, for the elastic curve, so we have positive moment here, then negative moment. So concave up, if this is the upper fiber, concave up curve. Then for this portion, concave down. Remember that we are viewing in that direction. This is the upper fiber. So concave up, concave down. Then we have negative moment, concave down first. Positive moment, concave up. Then negative moment somewhere here, concave down. Then negative moment, this one, we have a point of inflection here. So concave down. And for this portion, positive moment, concave up. You look at in that direction as positive. This is the upper fiber. So that's it. That's for this problem on the construction of shear moment diagrams for frames.